Hi, my name is Lindsay Ehrlich, and this is my Physics Lab 4 report on bar magnets. As a brief introduction, the purpose of this lab was to observe how changing the orientation and distance between a magnet and the observation location affects the strength of the measured magnetic field. We found that as the distance from the magnetic field increases, the strength of the magnetic field decreases, and when the observation point is parallel to the magnetic field is twice as strong as when the observation point is perpendicular. And we'll get into more of the concrete number calculations later. The fundamental physics principle that we used was the Biot-Savart law. So we have formulas for measuring the magnetic field from any location when the observation point is perpendicular to the dipole and when it's parallel to the dipole. And it's important to note in these formulas that mu is the magnetic dipole moment. So the setup was first to download the magnometer app and then align it with the Earth's magnetic field, and then also kind of calibrate the magnometer. So the system was the magnometer, and the surroundings were the bar magnet and the Earth. First, we wanted to take some on-axis measurements. So we aligned the phone and moved it only along the east-west axis. And then we wanted to find the distance where the x component of the magnetic field is 20 microteslas. And then we recorded and repeated that 3 times. And then we repeated that entire procedure for 70, 120, 170, and 220 microteslas. Then we wanted to take some off-axis measurements, so we adjusted the phone until the net magnetic field was 100 microteslas, placed a perpendicular meter stick there, which you can see in the picture on the right. We aligned the phone and moved it only along the north-south axis that we just established, and we recorded the x, y, and z components of the magnetic field. Note here that the z component, we can basically just ignore that. Here's the data. The main takeaway from here is when we plotted the data, we got the equation y equals negative 2.3812x minus 13.658. So we can tell that in the formula, the absolute value of b bar equals k r to the n is negative 2.3812, and the natural log of k is negative 13.658. We also calculated mu equaling 5.853 using the B parallel formula from our fundamental physics principle, the Biot-Savart law. Then we wanted to compare our observations to an ideal computer model. So here's the code for that. First, we're just setting up physical constants and creating a magnet object. Then we're defining a function to output the magnetic field given mu and r values. Then we're setting up observation locations at which we'll later compute the magnetic field. So that's just all the setup for that. And then lastly, we define the off-axis distance of the magnometer and plug the value into the magnetic field formula. And this was the output from that code. And so we can see here that the computed off-axis field is 2.52606 10 to the negative fifth, 7.57818 10 to the negative fifth, and 0 teslas. And our observed off-axis field was negative 6.6 10 to the negative fifth, negative 6.1 10 to the negative fifth, and negative 4.56667 10 to the negative fifth teslas. So there's a bit of a discrepancy there, and we'll get into some sources of error as to why that might be. So possible sources of error are other magnets were in the area, such as electrical cords. The phone was not perfectly aligned with Earth's magnetic field, and the phone was rotated slightly as we moved it along the meter stick. So the additional questions, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? My answer is that in this case, both the Earth's and the bar magnet's magnetic fields would contribute to the net magnetic field that the magnometer is reading, so we would not have been able to differentiate between the contributions, so ultimately the experiment would be invalid. The second question is, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? My answer is the principle of superposition allows us to conclude that the magnitudes measured in this experiment would double because the magnetic fields produced by each of the magnets would add together. Thank you for listening.